So hopefully you enjoyed the Gaussian elimination homework. We're going to go over number 32. That one was an even problem, and it should have had infinite solutions. So we're going to look at that, kind of make sure you understand how to write the solution when there's infinite solutions. Today we're going to look at systems of equations that are called non-square systems. We'll talk about how to solve those. And we're going to do a couple of application problems as well. So an application problem can create 3 variables and 3 equations, and we'll work through that. We are going to review using the calculator as a great tool to help check your work with matrices. We did that last year in section 3.8, which would have been probably early October last year when you did matrices in chapter 3. So we'll review how to use the calculator and the matrices of the calculator. So if you want to take out your calculator and have that handy, we will be using that. And everybody at home too, have that calculator handy, because we'll go through reviewing how to get the matrix in your calculator. And it's a good tool to use to definitely check your work. But there will be, like, the one application problem has decimals, and it's easier just to throw everything in a matrix and a calculator when you're dealing with a whole bunch of crazy decimals in an equation, a system of equations. So your homework tonight is a little bit of calculator work and then algebraic work. Please make sure you are following the directions that I've posted in Google Classroom for the assignment. I have it up here as well, but like the first 2 and the last problem, you're going to use matrices, and the ones in the middle, you have to solve algebraically. Anytime you get infinite solutions, your calculator will tell you that there's infinite solutions using a matrix, but you need to be able to write that in the specific form. So the problems we have today, those groups of problems, 35, 39, 40, and 77, those problems you will have to do algebraically because they will have an infinite solution case in them. So let's start with 32 and work through one of those problems together so we can see what happens with infinite solutions. How do you get a problem to have infinite solutions? And how do you kind of work through and write those answers? So this is number 32. And just a side note, 21 and 27, no, 15 and 21 had solutions. 27 was no solution. 31 and 32 were infinite solutions. So the last 2 were infinite solutions. 27 was no solution. And then the first 2 had solutions. The first one already gave you Z, so that had to have a solution since they gave you a value. All right, so looking at 32, we're going to try and use this Gaussian elimination concept to help us solve the system. And again, our goal is to try and eliminate the X's in that first column. So the first equation is going to remain the same, but we want to wipe out the X's underneath it. To do that, Joe, how could I eliminate the 4x in the second equation? Yeah, he said you can multiply the bottom by -2. So you are allowed to use that bottom equation, or you could multiply the top by -2 as well. So either one of those work. So if you always want to use the top equation, that's fine. Or if you want to try and use one of the other equations, that's fine as well. So let's go with what Joe said. He said multiply this bottom equation by -2. So Joe, if you multiply the third equation by -2, what do you get? And your resulting equation, Joe, would be So you may not have the same resulting equation, and it doesn't mean that you did it wrong. You just probably used the first equation, and that's fine. Remember, there are many ways to solve in math. So our first equation is x plus 4z equals 13. The resulting equation that Joe gave us is 2y plus 15z equals 45. So we're replacing this second equation because we eliminated the 4x, and we're replacing it with 2y plus 15z equals 45. So if I go back to my original problem, to do Gaussian elimination, the next step would be to try and eliminate the 2x in the third equation. Here, how could we do that? Sure, multiply it by 2, multiply it by -2. I'm going to use -2 just so the signs are already there. So the top equation becomes -2x, -8z, and -26. And then we currently have the third equation. And Peter, when you combine those together, what is your resulting equation? I think it's 45. I think it's 45. So we have -2y minus 15z equals -45. So that would be our second resulting equation. So the first and the second. So with Gaussian elimination, there are 3 variables. We've used substitution twice to eliminate the x from the second and third equation, so that our 2 resulting equations contain both y and z. And that's the goal, because now I have 2 equations with 2 variables. And if I use elimination one more time, I should be able to eliminate one of the remaining variables to get a variable by itself. If I look at those 2 resulting equations, Parker, what happens if you add those 2 resulting equations together? You get 0 equals 0 because they're exact opposites. So a positive 2y, a negative 2y, a positive 15z, a negative 15z, a positive 45, and a negative 45. You end up with 0 equals 0. Hi. Thank you. It might be him. So if you have a case where it's 0 equals 0, yes, it means that there are infinite solutions. Those infinite solutions can only be in a specific pattern. So we need to write that pattern using the equations that are in the problem. And because usually we try and get z as the final variable, z equals 2, z equals 5, z equals -7. We're going to start with that third variable and say, let z be equal to a. So if you have infinite solutions, your first step after that, there is no more elimination. But the first step is to say, all right, I have to try and write a pattern for x, y, and z. But you can't use x, y, and z in the pattern because those are the variables you're solving for. So we need to use an arbitrary variable. And a represents any real number. God bless you. So the next step after saying infinite solutions is to say, all right, we're going to use that third variable and say, let that third variable z be equal to a. So then you go back to one of your equations that contain a z and plug that A value in for one of those two equations. And it doesn't matter which one you have or which one you use. Both of them have a Y and a Z. So I'm going to go with the one that's positive. So I would have 2Y plus 15Z equals, nope, not Z, how about A? I just said Z was now A, equals 45. So our goal is now to solve for Y, because I need an ordered triple. I need an X, we need a Y, we need a Z. So we have Z, we now need to solve for Y. So Jeremy, in this equation, how would you start to get Y by itself? Yeah. So subtract 15A and then divide by 2. So if I divide each of these by 2, I have negative 15 halves and 45 halves. You're not always going to have nice answers. Fractions exist. At this point, you know that fractions were pretty much all of trig. So now I have the Z and the A, or I'm sorry, the Y, in both terms of A. We still need to have X because my solution should be an ordered triple. So we need X, we need Y, and we need Z to be represented in terms of A. So Z is now just A. Y is the negative 15 halves. Plus 45 halves. We need the X. And the only equation that contains X, if I go back to the top, the first one is pretty easy to look at because it's just an X and a Z. So I wouldn't want to use the second or third equation if the first equation is the easiest one for me to use to solve for X. So I can take that first equation, which says X plus 4Z, well, we changed Z to be A, equals 13. So that means X, getting X by itself, is negative 4A plus 13. So that would be my third variable. So each one of those I still have to solve for. It's nice when you get a number for Z because then you're solving using a number. Well, we're still using a number, but we're using the number A, which you're like, yeah, but A is a letter. A represents any number. So you're still using back substitution. You're just replacing those variables with the number A instead of a physical number of 2 or 5 or 7, whatever it happens to be. So to finish my ordered triple, we now have negative 4A plus 13. So your final answer should be a pattern for your ordered triple containing A, not an X, not a Y, not a Z, but an A each time. And that A is based off of the Z variable. And then replacing Z in to find Y, and then replacing that in to find X. So we're still kind of going backwards through the problem, but you're going backwards using the value A. Questions? So then if I asked you to find 3 different solutions, you could pick any number for Z. So I could say, let A be 7, and you could plug in a 7, and you could plug in a 7, and then you could find an ordered triple. Or you could plug in a 2 or a 5, whatever numbers you want. But I could say, find 3 solutions. You pick a number, you plug it in for each A, and then you get an ordered triple. Questions? So we will look at more problems like this today that are going to have this solution, where it's not an actual numerical solution, but it represents a pattern for the infinite solutions they could be. Questions? Remember, at this point in the year, things will not necessarily come to you on the first time. You have to try a problem a second time or try it a third time. You're now reaching almost calculus. So the concepts are going to get harder and more involved, which is why you had 5 problems and not 10 or 15. But don't give up after the first time. You got to work through it. So in your notes, if you can turn to section 7.3 again. But this is day 2. 7.3 part 1, day 2. Because there's a 7.3 part 2. We're going to continue working with this Gaussian elimination. So we're not done with the Gaussian elimination. We're going to work on it tomorrow yet again. But I do want to show you and remind you how to use that calculator and matrices to solve instead of just using the elimination process. It's a great way for you to check your work quickly by just plugging it into the calculator. Uh-oh. So if you want to take out your calculator, we are going to try and create matrices from the system of equations. Okay, we'll see if this works here for us. Solve the system using matrices, check your solution. So, does anybody remember how to write a matrix using a system of equations? So when we create a matrix, we have matrix A, which is our coefficient matrix. We're going to have matrix B, which is our variable matrix. Actually, that's X. Oops. And then we'll have matrix B, which is our constant matrix. We're going to create an equation using matrices that has the coefficient matrix times the variable matrix equal to the constants. A matrix, remember, kind of is like little boxes. It's an arrangement of numbers. An equation can be arranged in a matrix. And the way we arrange that equation is essentially taking the 3 coefficients in the first equation and just placing just the coefficients in a line or equation on the top of the matrix. So our coefficients for the first equation are 1, -2, and 3. So we're going to take those 3 coefficients and write them as they are in the equation, just without the variables. So then, Hannah, the second row of coefficients would be? Yeah, there's not a Z, so we need to place a 0 in for it. It still has to have a number. And Hannah, the last row would be? 2, -5. Good. So this is called matrix A. That's all of our coefficients. And again, you're going directly across the row, listing the coefficients for each variable. This second matrix is our variable matrix. That shows us what we're trying to solve for. And those 3 letters are X, Y, and Z, because those are the letters in my matrix, the variables in the matrix. Finally, that is equal to our constant matrix. Peter, what would we have if we had a constant matrix? What numbers would those be? Yeah, 9, -4, and 17. So I still have the equation. It's just set up slightly differently in matrix form. So to solve for X, to get X by itself, you can't divide. So my equation says A times X equals B. You can't divide by a matrix. So it doesn't work quite like regular numbers. Instead of dividing, I can still divide by using the inverse matrix, because the inverse of multiplication is division. We're going to take the inverse matrix and multiply it on both sides of the equation to get the variables to be by themselves. So the inverse notation, remember, if I'm finding an inverse, I use that little -1 notation. So we're going to use the inverse matrix of A. That's our way of dividing. I was multiplying A times X, so I need to divide it out. With matrices, in order to divide, we're using an inverse matrix. And then times the constant matrix. So if you go to your calculator, does anybody remember where the matrix button is in the calculator, Parker? Yeah, excellent. Yeah, the inverse of X. And it's hard to see on my screen, but you're using second and then that inverse of X, X to the -1. Remember, we want to edit this matrix. So arrow over to edit and hit enter. Does anybody remember the dimensions of the matrix that we have on our page? Parker? Yeah, so 3. Whoops. By 3. And then your calculator should show up with a matrix and spots for each of those. So enter your values in to A. And then you're going to do the same thing to enter the values in for B. So I'm going to go second X -1 over to edit, but down to B. Parker, what were the dimensions for B? 3x1. Nice. So again, your matrix should look like a 3x1. And we're plugging in those constants, 9. -4 and 17. You want to go back, second quit to the original screen, that calculator screen. So you have everything entered in, go back to the original screen. Anybody have questions? So now we're going to plug in the equation. We plugged everything in numerically, but we need the calculator to actually do the computation. So you're going to, again, use second X -1. But now I already have it edited. I want the actual matrix A. So you're just going to hit enter and matrix A should appear in your calculator. But we're taking the inverse of this. So I need to use the X -1 inverse of X button. So I now have the inverse of A. I need to multiply that by the B matrix, which had all the constants. So one final time, second X -1. I now move to B and I hit enter. And my calculator is going to compute the inverse of A with B. And when you hit enter, you should have your solution as 1, -1, and 2. It's in matrix form. Make sure you write it as an ordered triple. So don't keep it as a matrix. Write your final solution as -1 or 1, -1, and 2. So it's a linear order triple. Do you kind of remember those buttons from last year? Just needed a little refresher. That was the same problem that we solved yesterday. We solved it using Gaussian elimination, and now we just kind of checked our work using a calculator. Questions? So you can check any problem with a calculator except if it's infinite solutions, because it's not going to actually give you that ordered triple with the pattern. So when there's infinite solutions, the calculator isn't really beneficial for you to use to kind of solve or eliminate any of the variables. Questions with using the calculator? All right, so we are going to look at that non-square system. Still talking about this Gaussian elimination. If you look at example 1, we have x minus 2y plus z equals 2, 2x minus y minus z equals 1. How is that system different from these systems that we did yesterday, Peter? It only has 2 equations. So we call this a non-square system. If I have 3 equations, I have 3 variables. It's a square system. 3 variables, 3 equations. I can then solve for each of those variables. When the system has 3 variables, but only 2 equations, we call it a non-square system. So it's a system of equations in which the number of equations is not equal to the number of variables. The most important part here, it says this system cannot have a unique solution. What would that mean? Kaden, what would a unique solution mean? Yeah, so it can't have an original solution of 1, 2, 3, 1, negative 1, 2. You will never have a numerical solution of just one single point where they connect. So a unique solution is 1 point, 1 answer. Because they're not 3 variable or 3 equations, there's no way that you can isolate the 3rd variable to get it all by itself. But we can at least try and find a pattern for the numbers. So these will always have infinite solutions. So if they don't have a unique solution, then they're going to have infinite solutions. So our goal here is going to be to try and write the pattern for the infinite solution. So we're going to start off the same way that we usually would. We have 2 equations. We're going to try and eliminate the 2x in the second equation. That's the first step. So with Gaussian elimination, first step, that second equation, try and eliminate the x. Leah, what could I multiply the first equation by so that we can eliminate the x in the second equation? Yeah. So let's multiply it by negative 2. So negative 2x plus 4y minus 2z equals negative 4. Gianna, when you add those together, my new equation 1 and equation 2, what do you end up getting? What do you notice about all those? So what could you probably do with them? Yeah. So what would the GCF be? 3. They have a GCF of 3. So you could divide all of these by 3 and make the equation y minus z equals negative 1. It makes our numbers smaller. It reduces everything. So equation 1 is x minus 2y plus z equals 2. Equation 2 is y minus z equals negative 1. If there were a third equation, we would then try and use elimination to eliminate the x of the third equation. But there's not. There are just 2 equations. No matter how I try and combine these 2 equations together, I can never eliminate the third variable. So you could say, yeah, but look, I could try and eliminate the z here by adding them together, but then x comes back in. Because I could subtract or add the z's and they cancel, but then I have an x back into the problem. So there's never a way to get a single variable by itself. So there's no other work of elimination that you can do to solve this problem. So we used elimination once, but I can't continue to use elimination to try and eliminate to have a variable by itself because there's not a unique solution. So this is as far as we go. We can't change our system any other way. But I can write my answer using that crazy notation. And we're going to say, let z equal a. So anytime you can't go any further with an equation, if there's going to be infinite solutions, we will always make this statement. And you will see as you move further in math, you're going to see that statement where you use a variable and you represent that variable with an A or with an arbitrary value. So Z is going to be equal to A, but I need to still find Y and I need to find X. So you still have to find those other values, but those values are going to be represented by the letter A. So Brenna, what would you do next if we say let Z equals A? Yeah, so Y minus Z is now Y minus A. And then Brenna, Y is equal to A minus 1. So now we have a way to represent Y. Still using back substitution, I'm going back into the previous problem or previous equation. So Brenna, the last step would be take the first equation, x minus 2 times y. Well, y is a quantity now. Make sure you're multiplying by a quantity. A minus 1. Z is just a, and that's equal to 2. So I'm still finding the x, the y, the z, but we're finding it using the value a and still plugging that back in. So this becomes a negative 2a, a positive 2. Jack, if we combine all of our like terms, get x by itself, what do you end up having? So how would I want to solve for x. How would I get x by itself? Okay, move the negative 2a to the other side. The a to the other side. Yeah, so it's just going to be a. The 2's cancel. Negative 2 and plus a, negative 2a plus a. Take it to the other side. You just get a. So what does that tell you about x and z? They're going to be the same. So your ordered triple is a minus 1. So y is going to be 1 less than x and z. And then a. So a non-square system will never have a unique solution. There is no way that you can continue to use elimination because another variable is always just going to pop back in. You might eliminate one, but you're still going to have 2 variables. So you use elimination once and then you're done. And then at that point, you say, all right, can't go any further, but I need to write the solution with a specific pattern. So that let z equals a, and then you're still replacing that into the previous problem, or the previous equation. Questions?
About the calculator, I get the variables to show in my mind, put them in it, substitute it for zero.
Oh, you can't, so you will never put the actual variables in the box. You only put numbers in.
Oh, okay.
So they'll just represent those variables. So it's a representation of the variable. Always x first is x, second is y.
Okay, thank you.
Any other questions? So infinite solutions. If you end up with 0 equals 0, your pattern will always be written like this. If you have a non-square system, you're going to have to write a pattern as well. So there's one other problem that we're going to see if we can start together. And it isn't, there's actually 2. We'll do the third one tomorrow. This is an application. I'm still going to try and write a system of equations, except in this problem, it's giving us a quadratic equation and some points. So find a quadratic equation in the form y equals ax squared plus bx plus c. That passes through the points -1, 3, 1, 1, and 2, 6. Says you may use matrices to solve the system. So our goal is to come up with an equation that would be a parabola. Our parabola would pass through the points -1, 3, 1, 1, and 2, 6. And we're going to use a system of equations to help us solve this. So let's think about an ordered pair first. If you have an ordered pair, -1, 3, let's just start with that one. What does the ordered pair represent? Peter? X and Y. So the ordered pair -1, 3 represents the X and the Y. You can replace X and Y in for any equation and try and solve for the remaining variables or the remaining coefficients. So we're going to take our parabola equation, and instead of saying Y, we're going to use 3. I don't know A, but we know X is -1. I don't know B, but I know X is -1. And we don't know C. So we're going to take the variables, and we're actually replacing the variables in the problem. Usually it's the other way around. We know A, B, and C, but we don't know X and Y. Now we know X and Y, but we don't know the A, B, and C. If I simplify this a little bit, I end up with the equation 3 equals A minus B plus C. -1 squared is 1, giving me a positive A, a negative B, and a C. If you do that with the second point, I have 1 equals A, 1 squared, B times 1 plus C. I now have a second equation with A, B, and C. Remember, we're doing systems of equations, so somehow I have to make a system. And we have a third point. Notice 3 letters, 3 points, because I can create a third equation by plugging in X and Y. That gives us 6 for A, 2, B, and C. So a set of ordered pairs, actually, we have 3 sets of ordered pairs here, create a system of equations, 3 variables, 3 equations. It says that you can use matrices. So let's just go through that process of setting up the matrix. The first matrix would be your coefficients. This time we're solving for A, B, and C. So the coefficients would be the numbers in front of A, B, and C. So 1, a -1, and a +1 for the first equation. All 1s for the second, and the third 4, 2, and 1. We have the variable matrix, which we will never enter into the calculator. That's just the variables that we're solving for, which are not X, Y, and Z. They're A, B, and C. And then your constants are 3, 1, and 6. Once you plug that into your calculator and you get the answers, those answers represent A, B, and C. Those answers will create, when you plug them in a parabola form or quadratic equation. So you would have then 2x squared plus 3x plus 5. I will tell you that we didn't get to number 85 or we didn't get to example 3. Read through the problem, try and create a system of equations. We'll go through example 3 tomorrow, but try and work through it and see if you can kind of figure out how to create a systems of equations for that. Short factoring quiz tomorrow. Have a fantastic day.
Have a good day, Miss Kane.
Thanks to Darby.